And you can see some interesting things I post. Read them, they're useful for your project. So for instance, I posted a link about an article about how to do brainstorming, which will be important for your assignment too. And a few other interesting things. So you can take a look there if you want. Okay, so we are here, let's see. So last week you talked about geometrical optics. This is extremely important for the midterm, will certainly be asked. Okay, so make sure you're clear about it. And we have one review session coming up in 2 weeks. So, and it's mandatory for you to attend. So definitely come and attend. Yes? Ah, it's here. Anything is here. Everything is already planned out, remember? October 17th in class. Let's see. So very important thing before I forget, Apratim posted sample problems here. You see that link there? Click on it. Click on it, read through it. Try to do them yourself, okay? These are somewhat hard, but you will see the flavor for what we expect you to understand. Not a lot of math, but lots of conceptual things. A little bit of math, I would say. And the solutions are also there, but I would recommend you to first go through it without the solutions. Yeah? Yeah, go ahead. Yes, so one of the reasons for the review, the reason, for instance, we have 2 classes here. The review, sorry, wait, something happened. Oh, I thought I had an extra lecture, but I guess not. Oh yes, there is. So we have a midterm review here, but there's not enough time to actually do example problems. So that's why we have an extra class time here. This is important because this is probably the end of most of the optical engineering you'll learn. At least the things that I would like you to really understand in some detail. That's why we have 2 classes there. So try to come to it, yeah? And try to practice. And most students in most years tell me that's kind of the hardest part because it's something new, you know. It's not that it's difficult, it's just that it's different, you know. Okay, so today we're gonna talk about, let's see, non-imaging optics. So this is a little bit, so we're gonna split this lecture into 2 because it's an important topic. And I'll turn on the lights, a little dark. Oops. Oh, weird. Okay, it's an important lecture, so we're going to split it into 2 because I want to make sure you understand the concepts. So it's a little bit different than what you did last week. So let's jump right in. Let's see if I can hide this. Be up there. Okay, hopefully that's good. Okay, so very briefly, let's talk about imaging optics, which is what we learned last week. So let's review very, very quickly. So in imaging optics, we talk primarily about forming an image of something, okay, as the name implies. So what does that mean? That means you have an object, you have some optical system, and you're forming an image. Now, what does that technically mean? That technically means that you are forming a one-to-one map between the object and the image. So a point P of the object essentially gets mapped to a point P prime on the image or the camera sensor or whatever, okay? So every point of the object, so let's say I have this arrow, will get mapped to a point on the image, one point on the image. So it's a unique mapping. That's the ideal situation. But the ideal situation, of course, does not exist in reality. In reality, it's always a little blurred. You never form a perfect image. When you take a picture, it's always a little blurred. And the blurring is, think about it like a one-to-many mapping. So in reality, what happens is that you take light from a point P, and instead of forming image, converging all the light to a point P prime, you will instead get a little blur here. So there will be several points around P prime where the energy will be concentrated. That's in reality. So it's a one-to-many mapping in reality. Okay, so you should be aware of that. And I believe you saw a little bit of the aberrations and diffraction blur from last week. So just to summarize, light from point P is captured by the optics and imaged onto P prime. There is a unique one-to-one mapping between the points in P and P prime, okay? And every other point on the object to every other point on the image. Now, the key difference in non-imaging optics is that the goal is to create a desired irradiance on the receiver for a given light source. There is no one-to-one mapping of the points on the source to those on the receiver. So, okay, let's try to understand what that means. What that means is that in non-imaging optics, all we're trying to do is not form an image, but try to take energy from the light source and put it on a receiver. Another way to think about it, if I take one point of the light source, the energy from that point does not need to go on one point of the image. It can go anywhere on the receiver. Okay, so it's a fundamental difference, but it has some interesting implications. And obviously you can imagine the examples here, right? That the top one is, for instance, when you design optics, like glasses you wear, camera lenses and so on. And the bottom one would be luminaires for lighting, solar concentrators, headlamps for cars, traffic lights, things like that. Two different situations. One is imaging optics, one is non-imaging optics. Conceptually, that's the difference, okay? So let's see what this means. So again, let's start with imaging optics because it's easier to understand, okay? So let's look at a simple case. So we have an object, E, F. We have a lens. Let's call it a lens, but it can be anything, some imaging system, C, D, which is imaging onto, forming an image, AB, okay? So all the rays from F end up at A. And you saw if you have a single lens, the image is reversed, right? There is this reversal happening, just like a mirror, for instance. And all the rays from E end up in B, okay? And all the rays from P end up in Q. By the way, when I say all the rays, it's of course not exactly all the rays, because if this is really a point source, you should be aware that it's emitting light in all directions, right? But the lens is only capturing some portion of it. In other words, in reality, if you take a point, it will emit in all directions. And let's say I have a lens here. I'm only going to get the maximum angle it subtends. Everything else is lost, right? This, by the way, is one of the primary reasons why you can never form a perfect image. This will not be a single point, even though this can be atomically a single point. This will always be a little blurred. It's because of the fact that you haven't captured all the rays. A simple way to think about it. So you've lost some information. So also another way to think about it is imaging is a form of information transfer, right? You're taking information from one plane and putting it in another plane. And it's never perfect. You're losing some information. Anyway, so that's in non-imaging optics, of course, you lose a lots of information because you don't preserve the spatial information, right? Or the rays can go anywhere. Now, let's think here carefully. So if this is an imaging system, all the rays that are collected from F end up at A, the rays that are collected from E end up at B. So if I take any point in between E and F, like this point P, I can guarantee that the rays that are collected by the lens from P will end up somewhere in between A and B, right? Because it has to have a one-to-one map. It has to have a point on the image. So in this case, it's Q, okay? So light from F is concentrated onto A, E is concentrated onto B, P is concentrated onto Q, and then I can define a magnification like we saw last week, where the size of the image, DI, is M, the magnification, times DO, the size of the object. Okay, we saw this last week. And this magnification is because of this linearity, right? In other words, every point here corresponds to a point here, right? And that's why I can write a linear equation, di equals m times d naught, do, sorry. If it's non-linear, I won't be able to do it. Okay, so something to think about. Now we'll come back to this concept for non-imaging optics, but let's continue with imaging optics for a second. So of course, we know lenses are used in imaging systems. So a lens can be thought of as a surface, and typically we'll start with imaging one point. So you want to form an image of a point P onto Q. You want to define a surface here such that a ray which comes from P, after it interacts with the surface, will undergo refraction based on Snell's law and refract and bend towards Q. Right? We saw this last week. And based on the Snell's law, we can calculate what is this tangent of this curve here at that point. What I mean is the following. So if you take a ray of light and let's say you want to send it to this point here. Okay. Now I can draw this curve here in many ways, right? I can turn it many ways. But Snell's law restricts how I will draw this. So first of all, I'm just going to draw something arbitrary, let's say. So at the infinitesimally small distance, it's a line. So you can ignore the curvature. So first we'll draw a, this is not a good example. We'll draw a normal. By the way, this you should have done last week, but let's just redo it quickly. First, you'll draw a normal, okay, which is 90 degrees to the curve here. And this is our incident angle. This is our refracted angle, right? This is the refractive index inside. I'm going to assume it's air outside. And then sine of the incident angle is n times sine of the refracted angle, right? So I know theta r and I know theta I because I know these points. I know where they're going and where they came from. So by knowing these two, I can essentially determine, okay, what is my normal here? Okay, because I can draw a vector here. And of course, if this is in vector notation, some of you might like this better. It's n cross ki should be equal to n cross kr. And then from that, you can figure out n. Basically find the angle, okay? This is geometry. So once you find the angle, then you can draw the tangent to form the curve. And then you repeat it. You repeat it for another ray, right? And you draw another curve. Repeat it for another ray, draw another curve, and so on and so forth. And you finally end up with a continuous curve. So every point of that curve, you can calculate based on ray tracing. And of course, you don't do this by hand. You do it on a computer. The programs which will do this automatically for you, which is what you will learn in 2 weeks. There's a lecture on this. Okay. This surface is called what's called a Cartesian oval. It's basically a surface such that each point on it has only one ray of light from P. Okay. Every point here, of course, you can connect to P. So that's a unique ray. And it bends with another unique ray going to Q. Okay. So basically, the surface is chosen to focus all the rays of light from P to Q. Now, this gives rise to a very important concept, which is very important and very general. So it's important you understand this. This is the idea of an optical path length. Okay. So in an imaging system, the optical path must be same for all the rays. In other words, if you are a photon going from here, and you travel in straight lines, and you encounter this surface, and you bend and travel in straight lines to here, the distance that this photon traveled will be equal to the distance traveled by any other photon across any other rays. This is what's called Fermat's principle, and you'll see this in some of the examples that I just talked about. So optical path length, and you probably saw this last week, it also depends on refractive index. So for example, the path length of this line, PRQ, is D, the small d, plus n times D1, because D1 is inside a higher refractive index material. And that should be equal to capital D plus n times capital D1, where this capital D refers to this straight line, optical axis. And you can take any other ray, this will always be equal. Okay. And this was what's called the imaging condition that you solved in your matrix last week. So if you recall, you solved an image, you calculated an imaging condition, and you calculated the lens maker's formula, 1 over U plus 1 over E, V equals 1 over F. This basically comes from this principle I just mentioned. Okay, you set the optical path length for all the rays to be the same in your matrix formulation, and you end up with this equation. So you just need to understand it conceptually, yes. What do you mean actually? The numbers are the same, yeah. So you take the D and take the D1, but then you have to multiply it by N. The reason to multiply by N, by the way, did you talk about this last week? Any guess? Exactly. The light will slow down inside the material. So it's the time that matters, right? So you're trying, all the rays take the same amount of time from this point to this point. So if you make this, time is, yeah, the time. So this is non-relativistic. So we're going to assume time is absolute. It's actually not strictly true for obvious reasons, because in relativity they're connected, but let's put that aside. In non-relativistic optics, time is absolute. So the time it takes for a photon to go from P to Q is the same, independent of whatever path it took. And then it comes from many fundamental theories, let's say. So, and you can prove, of course, time is what? Time is the same. So time is velocity, distance divided by velocity, right? So the actual physical distance divided by velocity. So physical distance inside the material, let's say, is D1. The velocity inside the material is velocity in vacuum divided by the refractive index, right? And in air, D naught divided by C, right? So if I simplify this, this becomes N times D1 over C plus D naught over C. This is the time taken by the photon from P to Q. Doesn't matter what the ray is, it'll always be this. So this is equal for all the rays, but of course C is a constant, so we can just get rid of that. So that's how you get the Fermat's principle. Okay. Again, you don't need to memorize any of the stuff, but just think about it, and you'll see this more in the practice problems as well. So it'll help you kind of get a feeling for it. Okay, now we only talked previously about imaging 1 point. What if you want to image 2 points? 1 point is not very useful, right? Doesn't form a good, decent image. Let's say you want 2 points. We can actually show that you need at least 2 surfaces to image 2 points. In fact, this is something you can prove yourself because it comes simply from Snell's law. 1 surface can only be true for 1 point. If I take another point here, let's say this is your face, and that's your nose. Is your pretty smile. If this surface is perfect for your nose, okay, it forms a perfect image of the point on your nose. If I take a point on your mouth, the surface won't work anymore. And you can prove this yourself because it's simple geometry. You can draw a ray and see, and you will show that it has to form here. It's not going to bend the right way. Because this point here, for instance, is designed for that point, right? Not for this point. Okay, remember how we drew it based on Snell's law? It depends on this angle right here. But if I start drawing another ray here, it won't satisfy Snell's law based on this tangent. You need another surface. You need one more surface here, which is what's coming to. Okay, but of course, one more surface is only good for 2 points. 2 points is still not good enough, right? You need more, which is why one way to think about it, if you take the camera out of your iPhone, it will have 6 or 7 lenses. It's about 14 surfaces, right? Each lens has 1 surface. two surfaces, sorry, well, front and back. And that's the reason, because well, it's not the only reason, but you can conceptually think about it as a reason. So you're trying to correct for all the points. So your selfie looks beautiful everywhere, right? So one way to think about it. Of course, this is all done with a computer nowadays. No one does this by hand, but I want you to understand the concept of why we do this. Okay, so let's see what this means. So I didn't draw a nice picture here, but you can imagine that's one surface of a lens of an imaging system, and this is another surface of an imaging system. And the rays are simply interacting with both of them. So for instance, this ray from F refracts from this surface, then again refracts from this surface again, and goes to A. Same thing happens for this ray, here, and so on. And in all cases, if you take the optical path from here to here, from here to here, from here to here, and I add them up, they will all be constant. So the Fermat's principle has to apply whether you have an infinite number of surfaces or one surface, doesn't matter. Okay, so that concept is very general, and that's why you should appreciate that. Okay, we don't need to we don't need to beat this horse too much, but just appreciate that this is an important idea. Two surfaces can be designed such that 2 points are imaged. So in this case, F goes to A, E goes to B, but the other points on the object will not be imaged perfectly. So these surfaces are now designed only for those 2 points, but in between, they won't be perfect. And this is, for instance, example of aberrations. When you take a picture, it's not perfect, usually, on your phone today, it looks perfect because there's a lot of algorithms after the fact, after this data is collected, lots and lots of algorithms which go to post-process, image processing algorithms, signal processing algorithms for the electrical engineers, which go on to essentially make it as aesthetically pleasing as possible. That's really not reality, if you think about it. Okay. So if you actually want to do perfect imaging, one would need an infinite number of surfaces or some perfect control of the refractive index. And this idea is actually not completely true either. It's still evolving. People are still trying to prove. In fact, my lab is actually trying to prove this wrong today. We have some projects. So I hesitate to say this statement, but this is what you were supposed to learn in undergraduate physics. So this is traditionally what is understood. So anyway, real lenses form imperfect images or images with aberrations. Okay, so that's conceptually the way to think about it. Okay, now let's see how this these two ideas that we talked about in the last 2 slides can be extended to non-imaging optics, okay, which is the goal here. So the non-imaging optics, we have a source like the sun, okay, shown on the left, and we have some optical system. Let's call it a lens for now. And then you have a solar cell, let's say, it's a receiver, okay? So our goal is to simply take all the rays that come in between F and E, okay, and send it somewhere between A and B. We don't really care where it goes. Pretty straightforward to think about it, right? Now, there are some things we can use to take advantage of what we learned from imaging optics. So if you think about the edge points, which are E and F, so E and F define the edges of the source, okay? And let's say we design an optical imaging system for those 2 edge points, okay? So in other words, I ensure that all the rays from F that are collected by my lens, let's call it, ends up at A, and all the rays from E ends up at B, which is easy to do, which is what we just did. We just talked about having 2 surfaces, being able to design perfectly for 2 points. Okay, let's just say we do that. Okay, then we see a very interesting conclusion. If I take any other point in between F and E, by principle, we can show, or by theory, we can show that any point here, its rays will end up somewhere in between A and B. Okay, So let me state this again. Once you understand it, it's a common sense, but until you understand it, it can be a little confusing. If you have an optical system where I take the two edges of the sun, for instance, I'm trying to collect energy from the sun. If I take the edges of the sun, let's say just take 2 points on the edges and design an optical system which perfectly image those 2 points onto my solar cell, then that's by itself is an ideal non-imaging system, because anything in between automatically will end up in between those 2 edge points. This is called an edge ray principle. Okay, so you have to think about this a little bit. Let's draw it to understand a little bit better, I guess. Let's imagine that's the sun. Okay, and I have some imaging system here. Doesn't matter what it is. I have a solar cell here. If I ensure that the rays here, so I'm going to draw this ray with a different color. This, okay, that's what a lens would do, right? And let's say I take this ray. Okay, that we can do, right? 2 points, 2 surfaces. Now, all I'm saying is that if we do this, anything in between will send out a bunch of rays, right? All directions. Whatever is collected here will end up going to this receiver. And the reason is because the edge points are mapped to the 2 edges of the receiver. So anything in between has to go in between. It may not go to a 1-to-1. In other words, may not form a perfect image of the sun, but you don't care. That's not your goal. You're not trying to form an image of the sun or the solar cell. Just trying to transfer the energy. Okay, and we'll apply this so you'll see what this actually means. So of course, a lens does this, right? If I design a decent lens, it will form an image of the sun, which by definition automatically is also a non-imaging optic because I've collected the energy as well, right? In other words, imaging optics is a type of non-imaging optic. So non-imaging optic is the bigger circle. If I draw a Venn diagram, non-imaging optics will be out here, and imaging optics is actually part of non-imaging optics. Another way to think about it. However, this is a little bit of a simpler problem, as you will see. So the lens, if you think about this as a lens, then it's simply a concentrator. The image may be formed if you want, but it doesn't need to be formed. There is no 1-to-1 correspondence between the points on the object and those on the receiver. This is a simpler design problem. Okay, you don't need to get that perfect match, essentially. You're just trying to get energy from one surface to another surface. Okay, so let's look at one more concept and then we'll look at some examples. So it's a little bit easier to understand. Okay, so let's imagine the source is large and far away, which is the case in the case of the sun, right? It's almost infinitely far. Then the rays are parallel. So you probably saw this in last week's lecture. If I have a point source, of course, these are spherical waves, right? It goes as a sphere everywhere, right? This is a sphere in 3 dimensions. But if I go far enough away, right? If I go infinitely far, it looks like a plane wave, right? You lose the curvature because it's so far away, it just looks like a plane wave. And this plane wave is represented by parallel rays of light. Okay, that's a plane wave. In other words, this will look like that, right? So when the source is large and far away, we define an angular extent. So of course, the plane waves can have angle, right? They may not be perfectly straight, so they come at different angles. So another way to think about this thing that I drew here is instead of having spherical waves, which is kind of what I drew here, if this is infinitely far, you basically have, it'll look more or less like not such a, this is so far away that this will basically look like that. And this side will basically look like that, okay? Because this is so far away. And then you define an angular extent. Right? There's an angle that is coming in. A cone of angles. A cone of light rays coming in. Okay? The edges. Defining the edges of the source, in this case, the sun. And this cone is very important. We'll come back to this. This is, by the way, the reason we have to track a solar concentrator follow the sun, because it'll fall out of the cone, right? So think about the solar concentrator like you're only seeing that much of the sun, right? So the sun moved, and the concentrator did not follow. It'll fall out of the cone. Okay, so the concept is quite simple. So you have parallel rays D1 are focused onto A. Okay, that's fine, just like a lens. Parallel rays D2 are focused onto B. By the way, I don't know if Apratham pointed this out, but let me point out something very quickly. If you take a normal lens, and if I send in parallel rays, of course it forms a focus, right? So you should know this by now. Now, if I come in at an angle like that, what happens on this side? It will still focus, but because it's still a lens, but it will shift. So it'll focus down. It'll shift down. Okay, and of course this is easy to show. So yeah, I don't have a good source, but if you when you get a chance, if you're outside, take a lens, like if you have glasses or any lens, you can form an image of the sun like a spot, and just tilt it. See what happens. Yeah, the spot should move around. That's this. Okay. And there is a simple equation for this. If that angle is theta, this is F times tan theta. It just comes from geometry. Very, very simple. This is the focal length. Okay, we'll come back to this again. That's true for a lens, not for a conventional non-imaging optic. Okay, so that's exactly what's happening here, right, in this picture. So this is coming at some theta, so this is shifted down from the optical axis. And this is coming at a negative theta, so it's shifted up on the optical axis. So all the edge ray principle is saying is that any rays in between, okay, any angles in between will end up in between. That's it. It's exactly the same as what we talked about before, except now that the object is at infinity, or really far away. So let's make sure we understand that. So if the edge rays, parallel rays D1 are focused onto A. Remember, that's one edge of the sun, let's say. Parallel rays D2, the other edge of the sun, are focused on B. Then all rays in between, which is all the other points of the sun, okay, will end up in between A and B, but need not be focused to points. Okay. Now we'll apply this idea to design something called a compound parabolic concentrator. Okay, so this is the next topic that we have to address. And we'll go through this conceptually and a little bit of math, but not too complicated. But let's first take a look at what the compound parabolic concentrator is. So it's just a short video. I will narrate it because the volume won't play. So obviously this is something you can buy. It's called a compound parabolic concentrator. So it collects light from here, concentrates on the other side. So you can see it's very bright here. It's taking light from there down here. So it's a rotated parabolic shape. The wide end collects the light and reflects inside. We'll see that. And it gets concentrated at the bottom. And they have an acceptance angle. Okay, so in other words, there is a range of angles that can collect. We'll see this again. So these are used in solar concentration, but also in things like telecom. So when you're trying to collect light from fiber to fiber, you use these kinds of things, or from free space communications. So for instance, in many rural areas, there's this technology people use, free space optical communications with laser beams. So you send a channel with a laser beam, you have to collect it. A CPC is often used to collect it onto a receiver. And there's many other applications, for instance, in biomedical imaging as well, inside your body, for instance, with the endoscopy and things like that. That's the basic idea, okay? Now let's see exactly how it works. So first of all, the goal, what a CPC is trying to do is to simply increase the concentration factor. So if you recall, the CPC looked like it had a wide end and a narrow end, right? Kind of like that. So if I write A as the area of the wide end and small a as the area of the narrow end, the concentration is simply the big A divided by small a. I'm collecting energy over a large area and putting it on a small area, right? Concentrating it. Okay. So the design goal is to concentrate the incoming radiation to the maximum extent possible with the highest efficiency possible. So that's the goal. Straightforward. Okay. So let's see. We have a radiation source here. Edge rays are shown here. R2, R1. Okay. Theta is the angle that they're making with respect to the horizontal. Our receiver or solar cell is AB. And now let's say I'm going to put something. Let's say E1 is the angular extent or the input aperture of whatever we are going to design. It will eventually become a CPC, but let's try to design something. Okay. So first of all, what you want to do, if you look at this, is that you want to take this ray, you want to put something here such that it gets redirected to that edge, right? And you want to do an exactly symmetric thing on the top. The ray R1, you want to reflect down to B. Okay, everything was symmetric across the horizontal axis. So we only have to do one side, and the other side is just a mirror symmetry. Okay, so let's do that. And of course, and now it's turned around 90 degrees. Okay, so let's reorient ourselves. So AB is the receiver now, sitting like that. Okay, you can also call it the exit aperture, but doesn't matter. And this is the ray. This is the edge ray R1 coming in at an angle theta. I'm going to put a mirror. Okay, a mirror is the simplest way to deflect the light, right? You can put a mirror here at an angle beta, where the mirror is D1B. The ray R1 will intersect D1 and reflect by following the angle, law of reflection to the point A. Okay, this is the largest angle that I can reflect by, because otherwise it will miss the receiver, right? A is the edge of the receiver. So for maximum concentration, what do I want to do? So if I look, and of course I have a symmetric system here, so I have another mirror on this side. So the concentration here is simply the area C1 D1. Okay, this input area divided by AB, which is the output area or the exit input aperture divided by that exit aperture. Now I want to maximize concentration. So my receiver area is fixed. So all I can do is increase my input area. I can try to collect over a larger area. And to collect for a larger area, what can I do? I can decrease beta. Right? I can try to make this as small as possible, as wide as possible, like that. Right? The two mirrors. However, I cannot make it too wide, because if I make it too wide, I will lose that ray. So let's make sure we understand what that means. So I have my receiver here, AB. Okay, and I put a mirror here. Let's only draw one side. And I have a ray coming in, some angle theta. And let's say this is beta. And I'm going to say this reflects right now here. What happens if I turn the mirror down? Because what I'm trying to do, so this is D, right? Yeah, this is D. So what I'm trying to do that. Why? Because I want to increase the input aperture. I want to make this larger, collect more light. But what happens if I bend this down? What happens to the ray, I mean? Yes. So let's follow it, right? And law of reflection states that I should draw a normal here. This angle should be equal to this angle, and the ray will just go straight back. Okay, it will miss my solar cell. So there is a limit to what I can do. Simple geometric limit. Okay, and that determines my beta. That will tell me, okay, that is the largest I can do. And of course, I have the symmetric thing here. So this angle is also beta. Everything is symmetric about this axis now. Mirror symmetry. Okay, is that it? Are we done? Is that all we can do? No, but so any ideas? What can we do? We can add more mirrors and go up. Okay. In other words, I can now, let's erase all this so it's a little cleaner. Let's see this. Okay, so I'm done with this. I picked the largest beta, smallest beta I can. Okay. Now, but I want to collect more rays, so I have another ray coming here, right? Parallel rays, edge of the sun. And I'm missing it, right? It's gone out of the mirror. So I can add another mirror, try to collect it. Yeah. Now this mirror will have a different angle, beta prime, right? Because I need to redirect this also to this edge here. And since it's higher up, I need to kind of bend it a little bit more. Yeah, you can see that geometrically, right? Just in the drawing. And I can keep going, right? I want another one, I can put more. And so on and so forth. Okay, and of course the same thing happens here. It's all symmetric, right? Everything is mirror symmetry. The exact same thing happens on this side. You only need to study one side because the other side is exactly the same. Okay, so I want you to be able to visualize this, right? So it's pretty simple, right? Once you can think about it. Okay, so that's basically what's shown in the next few slides. So if this beta is too small, as you can see here in this example, the ray is missing the solar cell or the receiver and is just escaping. In this case, it hit this mirror and this went out of the system. The edge ray will miss the receiver. So what to do if you want to increase the entrance aperture? And I answered the question for you. We add more mirrors. So we add another mirror here. Okay. Then the ray here is now redirected to A again. So the goal is to maximize the new entrance aperture C2D2 and you keep going. So the next question is, can we go forever? Let's think for a second. What will happen naturally if I keep doing this? You had the answers. Exactly. It'll start shadowing itself, right? It'll come in. Then it'll block the rays. Okay, do you see that? You can visualize it somewhat. And of course, that's where you stop because then there's no advantage in adding more mirrors. Okay. So So we can keep adding the mirrors, and you can imagine these mirrors to be infinitesimally small. In other words, I drew this like a long segment here, right? But in reality, it's a curve, right? I can imagine a tiny mirror, very, very, very small mirror, and every little segment is changing in angle, and essentially forms a continuous curve. Yeah, and that's a parabola. We can actually prove this, and we'll prove it quickly. So that's what's done here. So we can trace out a reflective surface or a curve, and you can keep in mind the symmetry about the vertical axis. Of course, there's a mirror symmetry. The angle beta has to be minimized at each point on this curve, right? Every point you're trying to minimize that angle so you can get more and more of the light. And this is also the curve that produces the smallest beta and the largest entrance aperture C3D3. So how big can you make this while collecting all the light? And this is the parabola. And you can see this from a very simple example here. Again, let's remind ourselves first what we're doing. We're taking all these edge rays, okay? These are the rays from the edge of the sun, and making sure all of them gets reflected onto the edge of the solar cell, A in this case. Okay, so let's now remember, imagine this picture. Now we're going to rotate it to make it a parabola. Okay, so you have to visualize it. So this was like this before. We rotated it down a little bit. So now the edge rays are coming straight down instead of coming at an angle. Okay, so we just rotated it, and everything goes to here. That's the edge of the receiver. Okay, now you can see this is the focus of the parabola. Okay, the parabola has its axis parallel to the edge rays, and its focus is at F. Now you can see a couple of things here, and you can prove this. This is very, very easy to do, but let's prove it in a very simple fashion, even no math at all, just conceptually. Remember our Fermat's theorem, where we said that the optical path length has to be the same for all the rays to form an image. In this case, the image formation is simply just a point. We're taking edge point of the sun and imaging it there, right? All these rays represent the edge point of the sun. Remember, it's just that infinitely far away, they're just all parallel rays. So this distance, Q3, P3 to F, okay? Keep that in mind, is equal, and that's all in air, okay? Everything is in air, is equal to Q2, P2, F, is equal to Q1, P1, F. And that's nothing but a parabola. So we learned this, actually should have learned it in high school, right? I don't know if you remember, when I was in high school, you could draw the parabola with a string attached to two focus, and then you kind of draw it. In other words, you put a point here, and then you draw the pencil like that with a string, right? Attach it to 2 points, and then you can draw. Actually, not 2 points, sorry. I should be very clear. You fix it 1 point, and this is allowed to move in a line. And then you draw. Okay, that's a parabola. And of course, you can prove this very easily because the equation of parabola is simply y equals ax squared, right? I won't go through it, but you can show this yourself just from the equation of the parabola. Anyway, so think about it. So now we're going to go back to the previous picture and overlay the two parabolae on top of it, so we can visualize this better. So here, you can see, first of all, let's identify the axis of the CPC, okay? Of course, it forms the CPC, I forgot to mention that. So that's the axis. And then this is one of the parabola, okay? And let's see, where is the edge ray? I can't see. So this is one of the edge rays, right? This goes straight to this edge point. And there is, of course, a corresponding edge ray, which is not drawn here, which comes parallel to that ray that we just looked at. and reflects off this point here, the entrance edge, and ends up at the other end of the exit aperture, right? And the same thing, of course, happens on the other side. So you have this ray. This ray goes straight to the edge. And let's see, should be one more. Yeah, I guess there is a parallel ray from this side coming here. It'll reflect off this point, and it'll come to this point. So this will take a little bit of getting used to, but try to visualize it. But I think you can kind of see, right? The rays coming here will end up here. Rays coming from here will end up here. Now you can see the parabola. So these two, first of all, they're not the full parabola. They're slices of the parabola. So you're ignoring the dashed parts. Okay, this two, then you rotate it to form 3D shape, and that's called a compound parabolic concentrator. In fact, what the exercise that we have done right now is actually a proof to show that this geometry is the best you can hope to do for concentration in 2D space. Of course, we only did it in 2D, not in 3D. Right? We only drew the things in 3D. So what we actually shown is that this is the best possible shape that you can actually get. This is the parabola, only in 2D. So just to remind ourselves, what is this? This is the entrance aperture of the CPC. This is the exit aperture of the CPC. The ratio between the entrance aperture and the exit aperture is the concentration factor. This is how much you're concentrating the light. Okay, very important parameter, right? When we are trying to design a solar concentrator, for instance, typically higher the concentration, the higher the performance of the solar cell. And we'll see this as we go along. Okay, so then this is something we talked about before. If we keep extending the parabola, of course, they will curve inward and the entrance apertures decrease and you'll get shadowing, right? So for example, C4D4, which is the extended part of the parabola, is smaller than CD, which means that now I'm starting to reduce my entrance aperture, which is not good. Right? I want to try to increase it. The rays will get shadowed, and you can see that, right? If I come in with the edge ray here, this will start blocking it, right? This surface will block it from hitting this other mirror. Okay, so we saw that before. So to reiterate, this is the key concept of non-imaging optics, this particular slide. So this is the key thing I want you to take from today's lecture, actually. The edge ray principle. So the light rays coming from the edges of the source must be deflected onto the edges of the receiver. So you only worry about the edges, everything else automatically falls into place. This is the nice thing about non-imaging optics. Okay, this is the basic design principle of non-imaging concentrators. So if you can take all the edge rays and put them on one end of the receiver, and all the symmetric edge rays and put them on the other end of the receiver, all the other angles in between will automatically end up on the receiver, but at different angles. You don't care, you just want the energy there. Okay. Now let's think about what happens if the angle is slightly larger or less than the edge rays. So let's do the example of the incident ray has an angle that is smaller than the edge ray. Okay, which is shown here. So my θ1 here is less than the theta. This is my edge ray angle, which is the angular extent of the sun, the edge of the sun, okay, let's say. Which, for instance, for us on Earth, on a clear sunny day, it's about ½ a degree. It's a very small angle, okay, small angle. Now what happens if a ray has an angle smaller than that ½ a degree? As you can see here, it will simply bounce off this mirror and end up in between. It's in between, so it's good, we collected that. However, what happens if a ray comes slightly larger? In other words, I am a different time of the year or something, it's January and you're closer to the sun. So the sun is slightly bigger, so instead of ½ a degree what I designed for, let's say it's 0.7 degrees, slightly larger. What happens? It will go outside. So that's what's shown here. Just a simple example, θ2 is greater than theta. It'll simply bounce around, bounce off, bounce off. This is obviously, I didn't do a good job with drawing, but basically it'll simply exit the system. And you can prove this also. Okay. Another way to understand this is that the CPC is designed for a fixed angular extent. Anything within that extent I can collect. If it's outside that extent, I lost it. Just keep that in mind also. It's not true for all angles, right? Okay, and we'll rephrase this shortly. So all rays entering the CPC with input angle less than theta are trapped and end up at the receiver, but all the rays entering the CPC with input angle greater than theta are lost out of the system, reflected back, whatever. So we can define what we call an acceptance for the CPC, right? Which can be thought of as a ratio of the number of rays reaching the receiver, or what's accepted, divided by the number of rays entering the CPC. And for an ideal CPC in 2 dimensions, it's a very simple function. It's a step function, right? It's 100%. All the rays are accepted if your theta is minus is within that cone, minus theta to plus theta, acceptance angle. And outside that, 0. Nothing is accepted. In the ideal case, and only in 2 dimensions. And theta can be thought of as the half acceptance angle. It's half because you're only 1/2 of the cone, right? So, by the way, when we talk about all this, we always refer to a cone of light, right? There's light coming in a symmetric fashion, and this is 2 theta. So your cone of light, one edge and the other edge. Of course, this is 2 dimension and 3 dimensions. It's a bit more complicated situation, and it's hard to do by hand. We'll come to that shortly. Now, we can also think about this. So this is the idea of the Fermat's principle, where we're trying to make the optical path lengths the same. So let's make sure we understand this as well, which I mentioned before, but let's just go through it again. So for a general parabola, we saw before, the distance AC, F, okay, which is AC plus CF, which is here, AC plus CF, is equal to BD plus DF. Okay, the distance of any point here to the parabola reflected to the focus will always be the same. This is the optical path length. This is the Fermat's principle, but also just the general geometric property of the parabola. Now, let's think about the CPC. Okay, so we have a ray here, ED. Okay, so that's the edge ray going from EDA, okay, which is this one, ED plus DA. That should be equal to CB to BA. Okay, so you have to think here a little bit because there's a different ray that I mentioned. So this is one edge. Okay, and follow my mouse here. This is the other ray. I'm assuming it's slightly hitting the mirror. It's an infinitesimal case. It's not an infinite, it's an asymptotic case. It's at that edge, and it's hitting that mirror and reflecting to the other end. Because just that edge of the parabola, right? And because this is a parabola, those 2 distances are the same, because visualize this as that. Just rotate it. Okay. And this is important because it'll give us a very important and simple result. So I can write that CB plus A2, where my A2 is the size of the exit aperture, is equal to ED plus DA. Now you can see by symmetry, CB, which is this line here, CB, is equal to DA, right? It's just symmetric, that is cross lines, right? By symmetry, we know they're the same. Is everyone okay with that? It's just a symmetry. They're the same, okay? So if CB equals DA, I can cancel this and that of that equation, right? I'll simply end up with A2 equals ED, okay? But ED If you look at this triangle here, EDC, ED can also be written in terms of A1. It's A1 times sine of theta. This theta is the same as this incident angle theta. Simple geometry, okay? So now I have A2 equals A1 sine theta. A1 over A2 is 1 over sine theta. Now what is A1 over A2? A1 is the input aperture. I forgot to mention that. And A2 the exit aperture. So what's A1 over A2? Yeah, what is that ratio? What do we call it? Yes, it's a constant. We can call it geometric concentration, concentration factor, concentration. Now what have we found out? The concentration factor is equal to 1 over sine theta. Now what is theta? It is the cone angle, remember? It's the acceptance angle. Beyond theta, I lost the ray. Inside theta, I collected the ray. Remember, we just talked about it. So theta is my acceptance angle. So now I have a very hard equation which limits concentration to acceptance angle. Okay. If I want this to be huge, if I want huge concentration, I need this to be very, very, very small. Theta goes to 0, which means that I have very small acceptance angle. Okay. So I want you to appreciate it. If I want huge concentration, I have to give up on acceptance angle. If I want huge acceptance angle, I have to give up on concentration. Exactly. This is a fundamental property. It comes from the second law of thermodynamics, actually. But of course, here we just calculated based on geometry, but this actually comes from the second law of thermodynamics. Okay. Now there's one more concept I want to go through. So yeah, this one we already did. So let's skip this. Okay. So the other part of the CPC we need to know is how tall is it, right? We need to really calculate. If we were to design a CPC, so I could ask you, design a CPC with a given acceptance angle, given concentration, we need to know entrance aperture, exit aperture, and the height, right? If you know those 3 numbers, then you can draw the parabola. So we have to relate the height. It's also a simple geometry. So because it's symmetric, we can divide this into H1 and H2. Okay, H is H1 plus H2. And H1 is simply A over 2, so half of that angle, divided by tan theta, just from this triangle here. Okay, and H2 is A2 over 2 divided by tan theta from this triangle here. So I can write H is A1 times 1 plus sine theta over 2 tan theta. Why? Because A2 is related to A1 as A2 is A1 times sine theta, as we saw in the previous slide. So it's just simple geometry. So we get a relatively simple equation here. So one thing you will notice is that this is wrong, actually. So let's look here. As theta goes to 0, which is when I want huge concentration, I said I can only collect this very small angle. My H goes to infinity. My concentrator becomes infinitely tall. And you can see that from this equation, right? As theta goes to 0, this denominator goes to 0. And this numerator goes to 1. So obviously this whole thing goes to infinity. And the opposite. So this is a typo. Theta increases, H decreases, or theta decreases, H increases. Okay. So for small acceptance angles, the CPC becomes very tall. Okay. So as I said before, the CPC is an ideal concentrator in 2 dimensions, but not so in 3 dimensions. In 3 dimensions, it's actually much more complicated, and you typically have to do this on a computer. And there are people who do this, and you can optimize it and so on. But from a very simple perspective, you have 2 options. You can either simply take an X and Y CPCs and multiply them together, which is what's done here. Or you can take one of the CPCs and just rotate it, make it rotationally symmetric, as you saw in the video before. Okay? The key is that in 3 dimensions, that nice acceptance angle, where it's 100% accepted inside the cone and 0% outside, is no longer true. you'll end up with a curve which looks more like a smoother variation. So you'll see something like, so in an ideal CPC, if that is my theta input angle, and then let's say that's my theta acceptance. In ideal CPC, I have this. This is my acceptance. So it's 100% is accepted. Outside that, nothing is accepted. This is 2D. In 3D, what you actually see, a gradual change like that. And the actual shape of it really depends on the details of the design. What this means is that you lose some of the rays here, and you actually gain some of the rays here. And this has to do with the skew rays. The skew rays refer to rays that are not parallel to any of the axes. So you can imagine a ray which goes in some funny angle inside in this three-dimensional space, right? Which might end up somewhere else. Just because it's not in the plane that you designed the parabola for. Because it's intersecting the parabola at some weird shape. Okay, so just be aware of that. Okay, I guess that was my last slide. So I just want to talk. I want to end a little early, but I want to make sure you're clear about the assignments. Assignment 1. So again, roughly 10 minutes. Don't go longer. If you want to make it a little shorter, it's okay. The key things are, make sure you address what I pointed out here. Try to be as clear as possible, but please ask me if you have any questions. As much detail as possible. Again, try to be didactic, but within the time limit. Yeah. And this is important research. Like I said, I'm kind of stressing it because it'll help you in the future assignments. So make sure you do it. Okay. So I think you guys know this. The last few minutes, I want to talk about assignment 2 instructions. So I've already posted this. So I know probably none of you have looked at it, which is fine. I just want to mention it, give you enough time. It is due October 3rd, so less than a month away. It takes time. That's why I'm trying to stress, and I'll try to remind you. Okay, so October 3rd, again, roughly 10-minute presentation. There are 4 points that I want you to hit for the next assignment. Number 1, I want you to identify 3 or more core problems with the current technologies. So in the assignment on Thursday, you're going to talk about all the technologies and maybe point out some of the problems. The second assignment, you're going to pick 3 or more, but let's say at least 3. And then you're going to brainstorm solutions to those problems. When I say brainstorm, you actually meet as a group, brainstorm, try to find solutions, okay? And you can go crazy, which is basically the best way to do it is on a board, right? Write down all ideas you get. You might, because the 4 of you, each one has 5 different ideas or 20 different ideas. Then you kind of discuss, okay, what are the good ones? You know, what are the crazy ones? What defies the laws of physics? Whatever, right? And don't defy the laws of physics. Number 2, list the results of your brainstorming session. You can take a picture of your whiteboard, for instance. It'd be nice, or just list it out, obviously. Present at least 3 innovations. I call them crazy or novel ideas. Be creative here, okay? That's the idea. That's the idea of brainstorming. It can be very creative. And there is no, let me put it this way, there is no silly idea or naive idea. Do whatever you think feels good. Right? Feels like you think will solve the problem. Then, this is the hardest part, in my opinion. You have to pick one idea to work on for the rest of the semester out of all that. So you have to champion one idea, okay? So pick your idea. Maybe more than one, but I would not recommend it because I really need you to dig deeper into that, whatever you pick, and describe it in some detail, not huge detail, but some detail, okay? And explain why you picked it, why you think it's novel, and what problem is it solving again, okay? Number 4, you could present preliminary calculations, simulations. I mean, you have about 3 weeks, 3.5 weeks. Some analysis of your selected idea. Be as quantitative as you can, but you can leave detailed analysis for the next presentation, which will really be a hacking. You can, assignment 3, if you recall, was to build something or do some very detailed simulations. Okay, I'm going to stop here, but let me know if you have any questions.